make an announcement about the copies of these things, of the Gifi book. And that is simply that I think the way that Kinko's probably expects to do that, I'm going to do this at Kinko's, is I'll take it there and it will be possible for you on, I think they said Thursday, or certainly Friday and later, to just pick up a copy from them, and you pay them for it. And that'll be the easiest. I'll let you know exactly how much it will be on Wednesday. I'm afraid I can't be here tomorrow, but I'll be here on Wednesday and the rest of the week. Also, somebody said that they had come from Duke and they had a very hard time finding a place to park. I would like to assure you that that's not because you're from Duke. So I wonder how many other people are having that problem. 1, 2, 3 other people?
I probably would have if I tried to find it.
You tried to find it. What did you do? Did you walk over?
My wife well, the visitors not want to accept it. It's just about half a block away.
Are you talking about
Just the other side of South Building.
if you drive? Did you try that? Anybody try the visitors lot? I didn't think about that.
Yeah, and if it is full, they give you permission to park down here, one of these other
I
lots.
think that's
Yeah.
the
Okay.
answer.
But there's still a fairly high probability that you will end up somewhere near Pittsburgh.
Castle Lyle's house, or you can park at Lyle's house. The visitors lot is up this road at the second stop sign. From here, you turn left, and it goes into a place where there's a gate, and there's a person in a little booth who comes out with a shotgun. If you're nice, you can get a permit, I guess, and
If
you
there's,
can't.
if there's space, you can stay there.
You can park right there.
No, let's send you down to the press building. It's right down here.
He says if you can park there, where they send you is to a parking lot that's just on the other side of the Arboretum, so in either case, it's only about half a block away.
You know, there are a variety of places that they may
They might
send
send you, including
and the
4A or whatever.
the distribution of the distance from here to where they send you to park has an extremely long tail.
You got infinite variance.
Anybody else want any comment on this topic?
Clearly.
We'll have a question? All right, does that mean that I won't try anything myself to take care of this problem unless I hear differently? All right.
Okay, we will slowly become more specific. The first part was about data analysis and statistics. The second part will be about multivariate analysis, which is a particular branch of data analysis and/or statistics. The first way in which I will try to approach or find a definition of multivariate analysis is to analyze the contents of 20 books on multivariate analysis. I hope this is readable. The analysis is taken from Gifi. Here are 20. Here are 20 books on multivariate analysis with the year in which they were published. And here are topics, subjects that these books do or do not cover. And the numbers in the table are the number of pages devoted to each of these subjects or topics. The topics are, it's not obvious from this table up here. The first one is mathematics other than statistics. So that's linear algebra, set theory, matrices, transformation groups. This is correlation and regression, B. I think it may be in the handout you have on data sets. I'm not too sure.
number 17, and it says there are 20 books and 7 topics.
Yes.
Illustrative data sets, does everybody have that one? That's the one with shortest,
Yes, well, it's mentioned briefly in the illustrative data sets as data set number 17. But that doesn't tell you what these labels are, so I will tell you what these labels are. The first one, as I said, is mathematics other than statistics. The second one is correlation and regression. The third one is factor analysis. The fourth one is canonical correlation analysis, D. E is discriminant analysis, classification, and cluster analysis. F is statistics. Statistics in the sense of distributional theory, sampling distributions, hypothesis testing, estimation. And G, finally, is the multivariate linear model. Now, there are many, many ways in which you can criticize this particular way of classifying the topics that occur in multivariate analysis books, but well, it's the one we use. That's the only thing I can say in defense of it. There are some things there which are taken together in one category which are not very similar. There are also things which are not in one category and which are very similar. The technique we applied to this matrix is correspondence analysis. Now, the table up here gives you the results of correspondence analysis, but that is not really very interesting to look at. Somewhat more interesting is the plot of the correspondence analysis solution. Now, one problem with this example is that I'm always discussing it before I've actually discussed correspondence analysis. So that, of course, is sort of the wrong way around, but the only thing you have to know about correspondence analysis right now is that if books, in this case books, you can also apply it to other objects as books, of course, but in this case books, if they have similar page distributions, then they're close together in the plot. And if topics occur in the same way in books, then they're also close together in the plot. And if a book pays a lot of attention to a particular topic, then it will be close to the topic point. The book point will be close to the topic point. So what you have here is a joint plot of books and topics. And the remarkable thing here is that there are 3 topics at the corners of an equilateral triangle, which I've also briefly shown here. This one. I'll go back to the other one later, so don't worry. This equilateral triangle has 3 topics as corners. So the topics that are statistics, mathematics other than statistics, and correlation and regression. And the books that are closest to these topics are the book by Thorndike, 1976, Gifi, 1981, and Green and Carroll, I think 1980, but I could be wrong there. No, 1976. And Gifi is 1977. I'm almost completely wrong on dates, but it doesn't really matter very much. And in the centroid of the triangle, we find the book or books by Morrison. There are 2 editions of that book, which are separate points in the plot. Now, correspondence analysis, another thing I should tell you about correspondence analysis here is that the way we have used it here, it means that the books are in the weighted centroids of the topics they pay attention to. So if a book pays 90% attention to correlation and 10% attention to statistics, then it will be somewhere over here, 0.9 times correlation plus 0.10 times statistics, 9/10 of the line towards this direction. In other words, in the way we have used it over here, correspondence analysis, and because all points are in an equilateral triangle, which is a property of the data in this instance, we can use these three topics as triangular coordinates that are familiar from many disciplines, I would say. So you can interpret the plot in terms of triangular coordinates. Show it again here. Here in this bottom corner is mathematics other than statistics and Green and Carroll. Here is correlation and regression, book by Thorndike, factor analysis, canonical analysis. Kendall's books are between correlation and regression and statistics on this line here, which means that there's very little linear algebra in it, basically. There's also a line from statistics to other types of mathematics. There's the book by Roy, and perhaps a little bit in front of it. Roy 57, and the books here in the middle pay attention in about equal proportions to all three major topics. So here we have some important distinctions in multivariate analysis that we have already discovered in our general discussion of data analysis, because they correspond with some of the principles of Ben-Zikri, for instance. There are books which pay a lot of attention to statistics proper. Book by Roy, the book by Gifi, and the book by Anderson, 1958. And here Kierkegaard. They pay a lot of attention to statistics proper. Then there are a number of books which pay a lot of attention to, well, there's actually only one book, which pays almost all its attention to linear algebra. That's basically because it's a book about linear algebra and not... well, and not as much about multivariate analysis. And there are more applied books which pay a lot of attention to canonical analysis, factor analysis, and correlation and regression. Thorndike, Cooley and Loans, Kendall, Dagnelli, that's French. Another book by Kendall. Well, a number of these books. If you want the details of the analysis, they're in Gifi. So again, it shows that the same distinctions we have already seen in our discussion, the distinction between statistics and linear algebra, the distinction between statistics and data analysis, sort of occur in this plot also. Partly, of course, because of the categories I have chosen, but also because it's clear that some books have a lot of inferential statistics and other books have a lot of linear algebra. The singular values down below here indicate the importance of the dimensions, but we will encounter them and see them many times when we're actually discussing correspondence analysis. I'm now using it mainly as a sort of an introduction to the distinctions you can make in multivariate analysis. Well, I'll now go briefly into the, let's say, the current approaches to multivariate analysis that are most popular, and perhaps that have been most popular in the past, but the recent past. The first one are multivariate analysis techniques based on the multinormal distribution. And there are some new recent books which could be added to the list. Gifi, again, is a 1981 book, so there are only books, and the analysis was already in the 1980 version of Gifi. So there are only books there which were written before 1980. There are now some books which are which certainly would be added to the analysis if we would repeat it again. The book by Muirhead and the book by Eaton are very good new books about multivariate analysis, which are strongly in the multinormal tradition, which means that it would be in the lower left-hand corner of the plot. Why is the multivariate normal distribution very important in multivariate analysis? and I'm assuming that most of you who are sitting here know that it is. The classical book is most important book, most influential book on multivariate analysis, is a book by Anderson, 1958, and it's almost completely based on assuming multinormal samples. Anderson himself gives 3 arguments, and they're listed here in black with red question marks behind them. He says that the multivariate normal distribution is usually a good description of data which occur in practice. Now, this may be true in biology, and even that is not, this may be true in some anthropological applications. For instance, if you are measuring the height of fathers and of sons, but it certainly is not the case in many other applications in the social sciences, for instance, in which you have to deal with categorical variables or with highly skewed 5-point scales and variables like that. The second argument Anderson mentions is the central limit effect. If the variables that you are studying are the sum of a large number of independent effects, then these variables are bound to be normally distributed. Now, this is true, of course, but I don't think it's a very relevant remark, because I don't think that there are many cases in which you can defend that the variables that you're studying are sums of a large number of small independent variables. So we can sort of skip this and say that it does not apply in many situations that we are familiar with. And the other reason why Anderson mentions the popularity of the multivariate normal distribution is that it leads to simple formulas. This in a sense is true. I mean, there are many things that you can work out for the multinormal distribution that you cannot work out for more general distributions, or that become very much more complicated. And the recent popularity of, for instance, of elliptical distributions is due to the fact that some of these simple formulas still survive for elliptical distributions. But then again, it's a sort of doubtful whether something which is usually a very bad description should be used because it leads to simple formulas. It's, the fact that it leads to simple formulas is an important argument, but not very important from the data analysis point of view, I would say. And again, of course, if your questions are complicated enough, then even the multivariate normal leads to very, very complicated formulas. There are 4 reasons in red which make the multivariate normal distribution very important from a data analysis point of view. So I would say forget about 3 reasons in black. The 4 reasons in red are much more important. Regressions are linear in multivariate normal distributions. Now, the fact that regressions are linear makes it possible to summarize dependency by simple measures of dependency, such as the correlation coefficient. If a regression is nonlinear, then the dependency between variables is a much more complicated fact and cannot be summarized by a single number. Another property of the multinormal distribution is that independence is the same as uncorrelatedness. For general multivariate distributions, independence is much stronger than uncorrelatedness. Another one we like especially, of course, is that equiprobability, the contours of equiprobability of a multinormal distribution are ellipses. And ellipses are, of course, very closely related to Euclidean distance. So there's a very close link between the multivariate normal distribution and the ordinary geometry of space, Euclidean geometry. And that makes things related to the fact that regressions are linear and that mean is the maximum likelihood estimator and relations like this. It's all related to the fact that these contours are ellipses. Another important property, of course, is that the class of multinormal distributions is closed under linear combinations. Linear combination of multivariate normal variables is still multivariate normal. So these are important properties which are also important from a data analysis point of view, because they simplify not necessarily the formulas, although they also have that effect, but certainly the interpretation of the results. And there's only one problem left. All these beautiful advantages are sort of vanish, because the multivariate normal distribution is actually usually a poor description, at least in the situations that we are familiar with. And not only is the multivariate normal distribution usually a poor description, but as I already mentioned before, the randomness of the sample, which is another, let's say, important component of the standard statistical prejudice in multivariate analysis, the randomness of the sample is also very often a poor description of the way the data are generated or the data are structured. So this is really a problem, and of course it's not adequately dealt with in many of the classical multivariate analysis texts. Another very popular approach to multivariate analysis, it's very popular for the last 10, 15 years, is log linear analysis. And by log linear analysis, I mean a very large class of techniques which are not necessarily log linear in the strict sense of the word, but which have grown out of contingency table analysis. You need not use the log linear model or the log linear procedures which are linked with maximum likelihood. You can also use weighted least squares or other techniques, but the class of techniques is, I think, clearly defined. One argument you can have in favor of these models is that they are much more realistic than the multinormal. That's because they are non-parametric, of course. They do not make such strong assumptions. They do make, of course, the assumption of independent and identical replications, but they do not make the assumption of multivariate normality nor any other parametric assumption. They also have some disadvantages which I've listed in blue. They're not very good as data description techniques. These disadvantages are all related. By which I mean that it's difficult to interpret the parameters that are estimated in log linear analysis. Now, if you have a two-way table, it's not very difficult to interpret the parameters that are estimated by log linear analysis, but higher way tables with these interaction parameters that you may be familiar with present a problem. Log linear analysis in practice is only usable, that's a little bit strong, but tendency is correct, if the number of variables is less than or equal to 4. It depends on the number of categories of the variable, of course. If the variables have all only 2 possible values, then you can go easily to m equal to 10. But let's say in a sort of an average example, log linear analysis can only handle small number of variables at the same time. Related to the fact is that it's only usable if n, the number of observations, is very large. The reason why you must use these two things in combinations is the empty cell problem. Multinormal analysis is special because it only studies the correlation coefficients, which means the bivariate relations in the data. You only need to look at pairs of variables and study their relationship. In log linear analysis, you must study the complete multivariate table. Now, such a complete multivariate table has many, many cells. The number of cells is obviously equal to the product of the number of categories for each of the variables. So that grows exponentially with the number of variables. Now, this means that if you have a very large number of cells and not too many observations, then you have a very large number of empty cells. So you must have something which either n must be extremely large or m must be rather small. And then there is in log linear analysis the model selection problem, which means that there are, if you have 4 or 5 variables, many, many models in the class of log linear models that you can select. There are, well, I forgot these numbers, but there's a subclass of hierarchical models, and there are already thousands and thousands of hierarchical models in this subclass. So you're stuck with the problem, how do I select a model from the class of possible models, given the fact that I usually do not have the prior information to make this choice right away. That, of course, is if you know what the data come from, if you have constructed them yourself, the problem doesn't occur. But if you have very little prior knowledge, then the model selection problem is very, very serious. And classical statistics does not have any clear-cut rules for model selection, I think. Log linear analysis is an outgrowth, perhaps, or certainly an improvement of what is sometimes known as tabulary analysis. Tabulary analysis used to be popular until, well, yes?
Well, I had a question on the log linear analysis.
Yeah.
Given the common practice of categorizing what can be conceived of as usually continuous or approximately continuous variables in log linear analysis and the information loss that would result from that, where would you place that? Would you place that under decreasing the realistic nature of the technique, or under 4 as a data description?
Well, there's it's obvious that if you decrease the number of categories of your variables by grouping, basically, then you're sort of trying to amend this situation. You have a larger number of observations on the average in each cell. So you're doing it to solve or to circumvent the missing cell problem. There is, however, another rather serious problem with this categorization stuff, of course, which is that the model is not invariant under categorization. If you have a log linear model and you redefine your categories, then in most cases you also have to redefine your model, because the model that you originally had in mind doesn't apply anymore. So I would say that you could list that as an additional problem in the case in which you have continuous variables. If you have continuous variables, then you have to think about the categorization problem, because there's no natural way to handle continuous variables within this framework. You can combine things and combine aspects of multinormal analysis and log linear analysis, but within log linear analysis proper, there's no way to handle continuous variables, so that would be an additional problem. Yes? Okay, where was I? Tabulary analysis. That simply consists in computing all the bivariate cross tables of your data. And there are some special packages which do that for you and which create about that much output. No doubt there are some of you who still have these piles somewhere in a closet somewhere. It's very, it's close to the data. That's certainly an advantage. But it's at the same time, it's the disadvantage of these techniques, of course, as far as you can call them techniques. It's much too close to the data. It gives very heavy output. That's one serious disadvantage. But it's also more seriously formulated. The problem is that from that particular output, you cannot do very much what is called here integration, reporting, table selection, interpretation. If you have 50 variables, which is very common in survey research, of course, then you have in the neighborhood of 1,200 tables. And the guy who funded your research is only interested in a report of 50 pages. So you have to select some tables from these 1,250 tables. You can do that in many, many ways, of course. And it's not clear from the analysis itself how these tables are related to each other and how you should select interesting tables. So there's a highly subjective factor involved here, and if you're into this type of research, which uses this tabulary analysis, then sometimes it's not clear at all why people have selected some tables, have ignored others, and how these various tables are related to each other. So tabulary analysis is more or less with large data sets. Of course, if you have only 2 variables, there's no problem. But with large data sets, it's more or less a dead end. And for 4 or 5 variables, we now have log linear analysis, which has its disadvantages, but which is certainly a large step ahead. For more than 4 or 5 variables, we also have packages. And these packages can now do principal component analysis or the general linear model, multiple regression, for many, many variables. Now this is convenient, but it has also a serious disadvantage. It's limited to numerical variables. Now one of the reasons tabulary analysis was popular at one point in sociology, for instance, is because it did not make any assumptions about the measurement level of the variable. You typically had variables which were categorical, and that did not necessarily bother you because a tabulary analysis could be applied to categorical variables. These techniques, such as principal component analysis and analysis of variance, with qualifications, of course. The independent variables analysis of variance are categorical, but the dependent variable must be numerical. These techniques are limited to numerical variables, which means that they cannot be applied to important classes of data that, for instance, social scientists, but also ecologists and biologists and even chemists deal with. What is the net outcome of comparing these 4 different approaches to multivariate analysis? The net outcome is that there is a gap somewhere. We need techniques for data sets which are mixed level. That means that they have continuous variables, categorical variables, and categorical variables can be ordered with ordered categories or non-ordered. That's what we mean by mixed level. There are many, many more mixtures possible, but we'll come to that later. We also do not have many techniques for mixed level data which can deal with a large number of variables. We also do not have many techniques for mixed level data with a large number of variables that are not the result of a random sampling process. If they are, we could, of course, go back to the multinormal techniques, perhaps. Another requirement is that we want a class of techniques which uses what I call joint bivariate analysis. Now, to define what I mean by joint bivariate analysis, I think it's easiest to compare log linear analysis and tabulary analysis. Tabulary analysis only pays attention, at least in its most primitive forms, to the bivariate cross tables, to the bivariate marginals, to the marginal cross tables of the multivariate distribution. Log linear analysis pays attention to the whole multivariate distribution. If you want to pay attention to the whole multivariate distribution, you're in trouble if you have a large number of variables, because you get into the anti-cell problem. And that is why we want techniques which, at least as a first starting point, are jointly bivariate, which means they are based only on the bivariate marginals, on the cross tables of the data. Now this is the combination of options, of techniques that I will be talking about this week, at least mainly. They have these 4 aspects. Yes?
What are the goals of your analysis when the data are non-random?
The goals of your analysis when the data are non-random? To make a more economical or more satisfactory representation of the data than the one you originally had. And the one you originally had was a large matrix. And the goal, of course, is not, which is perhaps the reason why you asked this question, to generalize in some sense or another from a sample to a population.
Yeah, usually we're thinking about describing something in some stronger or weaker way. And loss is what we'd be describing as non-random.
Well, perhaps I could answer that with a very simple example. If you have a scatter plot, then you can draw a straight line through it. And this straight line is a more parsimonious or a more economical representation of the scatter plot. And you can look at the scatter around the straight line to evaluate how good a representation it is. Now, all this does not necessarily involve a stochastic model which tells you how this situation generalizes to replications that you might or might not have. But it does give you this straight line, which is in a sense a shorthand description of your data, or a picture of your data. Or this is the starting point is that data analysis is basically data reduction, which means that you want to have a large, difficult to overview set of numbers or relationships, and you want to represent that in a easier to visualize or to comprehend type of way. That's what you use a technique for. Yes?
I wonder, Jan, if you weren't having set up a very large straw man to spend the rest of the next 4 days on, because after all, it seems to me that these other methods these deficiencies you're citing are intended to draw conclusions from data about populations, and you're talking, it seems to me, about methods that aren't aimed at this at all. So you're talking about methods that aren't in any sense competitive with these other methods. I would never think of using doing multivariate analysis to describe a sample of data. I'm interested in drawing inferences, and I'm interested in drawing probabilistic inferences, and it doesn't bother me at all that my data may not be non-normal to the extent that the non-normality of the data may not matter at all. So if you say what you're interested in doing is simply describing a body of data, well, that's fine, and that may be a very interesting thing to do, but you're not at all competing with these other methods because you're not going to be able to draw conclusions, it seems to me, from what you're saying.
Well, you mean inferences. You said conclusions, but you meant inferences, of course.
Either way.
Yeah. No, I'm not trying to be competitive in any sense of the word. The only thing that I am maintaining, which is perhaps is that there are many techniques around that are presented as being confirmative and which are not confirmative at all. And that there are many people who pretend that they are making inferences and who are simply doing descriptive data analysis. And
Present company excluded.
huh?
Present company excluded, I hope.
Of course, everybody in this audience is automatically excluded, but I'm simply talking about general practices which are, I think, quite. There has been a great deal of discussion about this topic. No doubt you're aware about that, and some of it is documented in the Gifi book. And it's difficult to give. I'm not setting up a straw man which I'm going to attack in the next 4 days, because this is the only day I will talk about principles on this level of generality. So the next 4 days will be about formulas, techniques, examples, straightforward exploratory data analysis, without any polemics at all. But the point is that there are many other practices and many other approaches to multivariate analysis that you must compare with our approach in a fair way. And if you want to compare them in a fair way, you must put them in a proper perspective. And I've tried to present a proper perspective, which is, of course, necessarily not everybody's proper perspective. Yes, but we can get back to this problem, which is a very basic and fundamental problem. It's what the whole distinction between data analysis and statistics is all about. At some other point too. I mean, there are many possible points where this remarks like this would be welcome. Yes.
Can I make a comment?
Yes.
I don't want to go on. Just one thing I commonly say in this kind of question is I think that these techniques are complementary to other techniques that you talked about. And that when one uses one category of these techniques versus another is determined by the state of advance of the science that you happen to be involved in. If you are very early in this scientific investigation, then you're exploring your data because you don't know what's going on. But if you're very late in it, then you should probably be designing experiments and testing hypotheses.
Yeah, well, I'm always sort of hesitant to say that the two approaches are complementary, but because that sort of sounds like a compromise type of solution, which is not necessarily the best one. It's I think that in many instances in which I have seen so-called confirmatory techniques applied, they're not complementary at all. They're exactly the same. I mean, it's a different technique, but the way the technique is used is exactly the same as so-called exploratory techniques. And there's the distinction between the two that was Gifi's first principle is not as strict as is sometimes suggested. And I made a remark earlier, a question from that gentleman over there. Of course, it's technically true. If you have a lot of prior information, then you can have precise questions, and then you can use these confirmatory techniques with a less guilty conscience. But the situations in which you have a lot of prior information are not very familiar to me, I must say. People probably go to another department when they have a lot of prior information. That's very well, they might. Okay. So there's a gap, which by definition means that we're not competitive because we're just trying to fill a gap which was already there. Definition of multivariate analysis. The content analysis of the book showed us a couple of principles along which these books could be grouped. They also showed us some confusion. Now, the content analysis of the books is not only the analysis I've shown you, there is a more detailed content analysis of the book with many beautiful quotations in Gifi. And questions which come out of that content analysis are, is multidimensional scaling a form of multivariate analysis? Must we have a random sample in order to be able to use multivariate analysis? Questions of that nature. Now, we answer both questions with a firm no, it says here. So multidimensional scaling is not a form of multivariate analysis, and you must not necessarily have a random sample in order to be able to do a multivariate analysis. And this firm no is reflected in our definition. Multivariate analysis studies the structure of multivariables. That's almost tautology, I would say. Unless a multivariable turns out to be something very surprising, and it is not. The first thing we must define what we mean by a variable. A variable is a function which maps a domain of objects or individuals into a range of values. So there are examples given below. The domain of values could be the real line. Domain of values could be the natural numbers. The domain of values could be three religions: Protestant, Catholic, and Buddhist. And the domain of values could be something like agree, don't know, and disagree. The domain of the variable could be a finite set of persons, for instance, or of screws and bolts and tacks, as we shall see in one example. The domain of the variable could also be a probability space. In that case, the variable is often called a random variable. So what we have is a variable, a single variable, is defined here simply a function which gives a representation of a particular domain in some other space. Or, to use this example, for instance, somewhat more pedestrian way, you have a number of individuals, and of each individual your function tells you whether he's a Protestant or a Catholic or a Buddhist, whether he agrees, disagrees, or answers I don't know on a particular question, which is in that case a variable. So each variable is a function. A multivariable is a set of variables, a number of variables defined on a common domain. So now you have a number of variables. For instance, you have this question, do you agree with some particular issue, yes, no, or I don't know, and are you a Protestant, a Catholic, and a Buddhist? These are two variables, and the third variable is how long are you, and has domain the real numbers or the positive real numbers. And the three variables define a multivariable, a set of three variables, with domain these persons that you are asking these questions of, and with range the product of the individual ranges. So product of Protestant, Catholic, Buddhist, of agree, don't know, disagree, and of the positive real numbers for the length. Now an important fact, this ugly green thing here is nothing, is a spot. The important thing is that the rows and the columns enter, the rows and the columns, by which I mean the n elements of the domain and the m variables, enter in an asymmetric way into this definition. The variables define functions on the domain, and not the other way around. And this means, of course, that you have to have data with the same structure. You must have values which are assigned to a given set of objects or individuals by a number of variables. And in this sense, multidimensional scaling is not a form of multivariate analysis, because in multidimensional scaling you have classical multidimensional scaling. You have dissimilarities, square matrix, with square symmetric matrix with dissimilarity measurements, and the asymmetry between variables and objects is lost, is not there. So we're using multivariate analysis in this precise sense. This implies, by the way, that I will not talk about multidimensional scaling. I have done work on multidimensional scaling, as some of you may know, and if you were here and expect me to talk about multidimensional scaling, I have to disappoint you, because this will be about multivariate analysis, and I've just excluded multidimensional scaling from that domain, so will not be talked about. There are many people who say that multidimensional scaling is multivariate analysis, or is a part of multivariate analysis, or the other way around. A lot of confusion. But I think we must be sort of very careful to keep this basic asymmetry in the definition, because multivariate analysis obviously deals with variables, and variables are functions. So let's keep this in. Elliot?
Would a two-way chi-square table be multivariate in this sense?
Yes, a two-way chi-square table is usually derived from something which is n times 2.
Or two-way analysis of variance?
Two-way analysis of variance is usually derived from, let's say, 2 classificatory variables and 1 dependent measured variable. So 3 variables.
Or a multiple regression?
Multiple regression would certainly be multivariate
I
analysis.
think many of us would not, from a statistical orientation, would not call them multivariate methods, but maybe multivariable methods, which it seems to me fits in more with your idea of analysis of multivariables.
Well,
Because I would think of analysis of variance as a univariate method, not a multivariate method, or similarly a two-way chi-square analysis as a univariate method.
two-way chi-squared analysis is a univariate method. Now that's, well, it can easily be if you formulate, let's say, analysis of variance as is usually done in the general linear model tradition with, in the case of two-way design, two independent variables which are categorical and one dependent variable which is interval or measured. Then you have, in terms of my definition, a multivariable which consists of three variables, two nominal variables, and one one dependent numerical variable. So it would certainly come under my definition formally.
Well, I would think a correspondence analysis of books on univariate and multivariate analysis would support my position.
This is just a semantic argument.
Well, definitions usually are.
Sure, but it's an important one when one's talking about multivariate analysis, because it sets up what procedures you're comparing things to, and so.
Sure.
I mean,
Well, one of the consequences of my definition is that I will talk about two-way analysis of variance and about multiple regression. So,
and not distinguish them between.
and not really distinguish them from multivariate analysis techniques. No, no. They are distinguished in several respects, of course. I mean, the fact that analysis of variance has these categorical or nominal independent variables distinguish it from other situations, but only in that respect. They're all variables from this particular point of view. Now, one thing I can do at this point is to show you some examples of the data matrices that we shall be looking at. And it's for this purpose it is helpful to have this handout in your hand. Yes, I have to perform some fairly complicated operations here. This is an example of a data matrix which should not be taken seriously. It's from the book by John Hartigan, and in your handout it is Hartigan's Hardware, number 13. It's 24 objects. The objects are listed over here. They are nails, screws, bolts, tacks, and they are described by 6 variables. So we have here a multivariable consisting of 6 variables. Now, I'm not making any statements here whether these variables are independent or dependent or nothing of the sort. Just saying that these are described by 6 variables, and the 6 variables have a number of possible values, of course. These are the ranges of these variables. This is their domain. And the values, well, you can look at them. Bottom, for instance, can be sharp and flat. Head can be flat, cup, cone, round, and cylinder. And something can be either made of brass or not be made of brass. Now, this is an example of a small, not completely serious, but it's for illustrative purposes, small data set which shows you how this notation of domains and ranges is turns out here's another one which perhaps a little bit difficult to read, but I can tell you what it is. Banks and industries, number 4. These are 70 industries. Boeing, IT&T, Burlington Indian, Armco Steel, Honeywell, to mention some of the more prominent ones. And these are a number of banking firms. The entries of the table list the number of persons that the directorates of these industries have in common with the directorates, if it's directorates is the appropriate word, board members. The number of board members they have in common. So it's probably very difficult to read, especially for you in the back, but General Motors and Morgan have 3 board members in common. Most of the banks and the industries do not have any board members in common. Now this would be classified as arising from, not being, but arising from 2 varied data. The objects, or the individuals in this case, are board members, and it's classified whether they are belong to one particular, what industry they belong, that's the range of the first variable, and to what bank, board of a bank they belong, that's the second variable. So this is the cross table which arises from these 2 variables that you have. Again, I'm not making any statements about the stochastic structure that is or is not on the basis of this data matrix. This is the sphere of influence data by Levine. What was that? I thought I heard multidimensional scaling. Multidimensional scaling is not a form of multivariate analysis. Here's a completely different set of data which has to do with the religious behavior of the Japanese. Something else is boards of directors of banks and industries. These are 6 variables, 6 binary variables. Binary means that they only take 2 different values, yes and no in this case. The binary variables are of the sort, do you practice religious conduct, do you visit a grave, do you read scriptures, do you visit shrines? And people can say yes or no. There are 4,000 Japanese people who have participated in this, in answering these questions. And the possible answer patterns are, of course, 2 to the power 6, 64. Possible answer patterns, and here it indicates how many times they occur. This is one compact way of presenting the data matrix. Of course, you could also use this answer pattern here, consisting entirely of 1s, and write it down 42 times, because that's the frequency with it occurs. Then the next answer pattern, you write that down below it 33 times, and you wind up with a matrix of 4,000 times 6. That would be impossible to show on this transparency over here, so this is really much more compact. In a sense, it's already a form of data reduction. That's not a type of data matrix we shall be looking at. This is also one which is quite different. This is the Munzinger-Rhine data, which you can also perhaps find in your handout. Yes, it's number 21. The objects which occur, by the way, in a sort of a permuted order here, the objects are graves in an old graveyard. These are archaeological data. And the columns, the variables in this case, refer to objects of particular types which have or have not been found in this grave. So this 1 here tells you that the object corresponding with this row has been found in grave number 39. And the dots are zeros, which indicate that the particular object has not been found in that grave. The fact that this matrix is so beautifully banded is a result of the analysis. It's not something which...
Some examples of the things you were checking to see if they were there.
Some examples of the objects. I think they were all types of brooches or jewelry type of things. I have actually somewhere a picture of these objects, but I'm not very familiar with with brooches in general. I'm not very familiar with these old brooches. I'm not familiar at all.
So they actually went into the grave. That went into the.
Yeah, they were buried together with the person that is in the grave. And the question, of course, is that the person who investigated this wanted to know in what order these graves were built, dug. Yes. This is another example to show you that we should also talk about time series type of data. These are called the baby data. Number 2, the baby data. Here are 20 babies. And these are 4 activities that these babies have in sequential order. I mean, they start with stepping, and then after stepping comes standing, and after standing comes walking with help, and after walking with help comes walking alone. The number that you see in that table is the week in which they started that particular activity. So Martin didn't start stepping until he was 15 weeks old. And Irene May, 19. Well, you don't know these babies, so I won't go into detail. What's the variable domain structure behind behind this example is more clearly listed here. These are the same babies, only the transparency cut away their first letters. These are 70 weeks. In each week it is indicated in what stage that baby is. So Martin in week number 1, it's not actually week number 1, I took something like week number 13 or something. Martin was still not stepping, and Virginia was missing. I mean, the datum here for Virginia was missing. Virginia could have been doing anything, I don't know. And at some point here, 6 weeks later, Martin started to step. That's the first stage. This is not yet stepping, so it's really starts at week 0. And then Martin went from stage 2 to stage 4 right away. Let's check if that's true. Well, there's certainly a missing datum somewhere there. So this is the domain structure. The domain is obviously the babies. The variables are these 70 weeks in which the changes occur. And there's already, by definition, the case that this is always increasing or non-decreasing. But of course, some babies are longer in some stages than other babies. This is another type of time series type of data that we shall be looking at now. I think this is another important type which you may be familiar with. These are preference rank orders. In this case, the objects are 39 psychologists. And what these 39 psychologists have done is to order 10 journals in terms of how much they use the journal. So, well, I'll give you the list of the journals in case you're interested. Journal of Experimental Psychology, Journal of Applied Psychology, and so on. So, these psychologists order these 10 journals. Now, it's It's very common to analyze these data with multivariate analysis, these type of data with multivariate analysis or multidimensional scaling type of analysis techniques. And we shall also encounter these data in the future. Here's another very nice example which is similar to the hardware data, straightforward multivariate data you could call it. These are American states, as you all see. And there are 7 data which I got from Howard Weiner. There are 7 variables here which are from the social indicator statistics, chosen in a somewhat peculiar way. There's population, per capita income, illiteracy rate, life expectancy, homicide rate, percentage of people with high school who are high school graduates, and the number of days below freezing point. Now, of course, this is a variable which is somewhat different from the others. You would typically not use this as a dependent variable if you're trying to predict it from the other variables. There's also an error which I have not corrected yet because I don't know what the exact value is. That is 180 days below freezing point in Nevada. Well, the previous talk I used this data matrix in, everybody jumped up immediately and said, "What? 180 days below freezing point in Nevada? That cannot be true."
Well, compared to somewhere like Montana, compared to Montana, that you put some of these questions.
Well, at some point I will have to write to Howard Weiner to... this, of course, this number also has effects on the analysis, of course. So I'll have to... once again to show you that this is sort of the typical format of the data matrices that I can show. Here's car data. These are a lot of cars, mainly American cars, but also some Japanese and some European cars. Their price in dollars, their engine size, their mileage, and their weight. Again, this is typical multivariate data. Now, I'm saying this is typical for the data that I can show you, because if you look through the handout, there are many other examples of typical multivariate data which I cannot show because they are much too large. Now, they can be either too large in terms of the number of variables, or they can be too large in terms of the number of subjects. If all the variables are binary, we can sometimes, even if you have a very large number of subjects, and we already saw that in the Japanese data, you can sometimes still show the matrix, but there are many examples with 30,000 or 15,000 or I don't know how many objects or individual survey type of data, and of course it's impossible to show that in any sense of the word. So the only thing you can show there are the results of the analysis, which are often nice too. So this is sort of a sampling of data matrices that we shall encounter during the rest of the seminar. And there's more information about them in this handout. There's also much more information about them in the publications where they come from. The publications where they come from is only for, I think, for about 25 or 30% they're taking from Gifi. For the rest of the examples are taken from other papers written by members of our group mainly. And if you're really interested in an example, you can ask me for a copy of the paper in which the example is explained in more detail. Could be that it's close to your field of interest or something like that. And if it's not in Gifi, I can send you the relevant publication later on. All right, these were examples of data matrices. Multivariables, we've had that. Let's continue here. It is again the case that this is the start of something new. So perhaps if we have some slow questions, it will exactly be 5:30. I don't think it's very wise to start a completely new chapter. Were there any questions? Yes? Wait.
Now, I wouldn't be asking this question if it were not that one of your earlier answers to a question on your slide was indicated as being firm. But is unfolding analysis a type of multivariate analysis?
Yes. A firm yes. Relatively firm yes. Yes, I think it is.
Would it be...
Qualified yes. Qualified. No. It would depend on whether the let's say the structure of objects mapped by variables into ranges would still be discernible, whether you could still describe the data in those terms. So
just as an example, let's consider preference data.
Yeah. All right.
Okay.
Yes. Well,
Can one not claim that unfolding analysis is multidimensional scaling with missing data?
yes. One can claim that.
Then I claim that
That it follows logically from these two.
Multivariate analysis and non-multivariate analysis is no more clear than the distinction between, say, confirmatory and exploratory analysis.
Yes. Well, I realize that the distinction is, there are many data matrices which you can analyze by either unfolding or nonlinear principal component analysis, in other contexts known as the vector model. So it's already very clear from that. I mean, the fact that you can analyze the same data matrix with the same technique, which only has a different name, but gives you exactly the same results, that there is there cannot be a very sharp distinction between the two classes. And I agree with that. The only thing I wanted to emphasize is that it won't do to say that, what some people say, is that any matrix of numbers, an analysis of any matrix of numbers is a multivariate analysis. I think that if you want to use the word multivariate analysis properly, then at least there should be something which corresponds with variables, because there's something in the name multivariate analysis which corresponds with variables. So I tried to emphasize examples in which this structure of variables, all defined on the same domain, in which you can also add other variables if you had them, is relatively clear. Now, unfolding is a case in point. I mean, that's obviously the case in which the boundary between the two fields is least clear. So you're right. Unfolding is I would classify unfolding as a technique for doing multivariate analysis on rectangular data matrices. But still, that would not cover the case in which you have a complete matrix of dissimilarities which is symmetric and has no apparent variable structure in it. Unfolding is an asymmetric situation. You can treat it symmetrically by saying that it's a missing data problem, and you can also solve it in that way by using a computer program and sort of fooling the computer program that it's such a problem. But the unfolding situation is asymmetric in many cases. There's a different role of rows and columns, and that's reflected in the conditionality That's often the row conditionality or the column conditionality that unfolding problems have. Yes?
Can you name one statistical method that is not multivariate? I can't think of it.
Well, what are you computing the
I
mean?
mean, like a t-test.
A
Any
t
statistical inferential procedure, a t-test, two-group t-test. A one-group t-test, I suppose, would not.
Well, a two-group t-test would be a case of bivariate analysis, and the groups being one variable and the variable that you're testing the difference of being the second variable. So in that sense, a t-test is a bivariate and consequently a multivariate technique. It's not usually treated under that heading.
I guess there's a question.
There are univariate methods, by the way. I mean, if you're testing whether a population mean is equal to 0, then one sample problems.
I guess a question was asked before, and I guess I'm still not clear on what the answer is. What is the aim of these procedures? It's not to generalize and make inference about population.
No.
What is the aim?
Well, it's not. Its main aim in most of the applications that I'm aware of is not to generalize from sample to population. But it's perfectly possible to use the technique to generalize from sample to population. It's very easy to embed these techniques within statistical models that generalize from sample to population. I will show you many beautiful examples of such an embedding, but in many cases they're completely useless because the data are not a random sample from any population. So it's not the case that it's never, or that it's impossible to use these techniques for, let's say, inferential purposes. But it happens that in many cases these inferential purposes are not realistic because there is no population, or you're analyzing the population, or whatever you want to call it. I mean, the structure population and sample does not apply.
Well, of course, it's rarely the case in experimentation that you're dealing with a random sample. In standard statistical analysis, that you're dealing with a random sample from a population, and yet one's interest is drawing inferences to populations. I mean, certainly all the research that's done here on our Site 10 students, the interest is not in, there is no random sample, even from Site 10 students, and certainly the interest is not in inferring to what Site 10 students are.
Well,
But it seems
it depends.
very different from what you were talking about.
It depends on whether you're using the word inference in a sort of a technical, well-established sense or in a wide sense. If you're using inference in a wide sense, in the sense that you want a result which can be generalized and which you hope to find again if you repeat your experiment or whatever it was, then of course we want results which are generalizable, and we want inference in that sense. Because if you're using it in that sense, then all science uses inference. I mean, nobody's interested in something which is only true for the data set or for the particular instance or particular moment that you're studying. You want results which have at least some degree of generality. But if you're using inference in let's say in the narrow statistical sense, which of a random sample from a population, and making, as the saying is, uncertain statements about a population from certain statements about a random sample, then my claim is that such inference is possible only in a very limited number of situations.
Well, I guess I'm thinking of an in-between situation in which you are interested in making inferences to a population, but from a sample that obviously isn't a random sample from the population. At best, you may have random assignment to two experimental groups, but you certainly it would rarely be the case that your sample of subjects that you're dealing with is a random sample from a population. But it seems to me one could still make inferences of a kind that I think perhaps you're not concerned with.
Well, it could be that, I don't know. Perhaps I have great difficulty, I must admit, with the word population, as it is often used. I mean, I know the population is in the simple case in which somebody at the Central Bureau of Statistics has a table of random numbers and a list of inhabitants of the Netherlands, and he uses this table of random numbers to draw a sample from the inhabitants of the Netherlands. In that case, I have no objection at all to calling the population of the Netherlands the population, because that's a fairly obvious use of the word. But if you're using the word population in sort of loose sense, independent even, I mean you're using it even independently of the random sample, then it becomes sort of important how to define how you're using the word population to define the sort of generalization you're looking for. Now, I would have to judge sort of by the case whether it is the sort of generalization I'm looking for. Could be not. I mean, it sort of depends on how this particular population and how the particular form of generalization that you want is defined.
Do you use the concept of robustness of validity that Tukey has introduced? A robustness a bit different from the
technical
the consistency robustness, but an index of really general, the extent to which one can generalize, even knowing that there is not a random sample from a specified population.
Yes, well, we haven't actively used it, but it's certainly something which is very closely to the techniques or the tools as we would like to use them. There are many of these tools available at the moment, and it's difficult to choose from them, but this is one of them, of course. Yes.
Take one more question about here.
Okay.
My question is always along the same lines. I was a little confused about the book example that you've been using, where it didn't seem like, as you sort of laughed yourself, you had well-defined the population because there was a nonlinear, a non-statistical mathematics book run in, and that gave you a corner, and that just seemed like sort of a vague definition of a population. And then the data, the rest of the data seemed to fall along the line between correlation and regression and statistics. And in fact, to my mind, that just suggested that there was different priority given to the different discussions in those books. You didn't really explain the sample. And that is different from saying that there is vagueness in the border between the topics, correlation, regression, and so forth. So I wonder if you can maybe, in that context, explain a little bit more what your purpose is in using that kind of example for this point.
Well, the purpose in using this particular example is to show that, well, one thing that it does show is that, remember that there were 7 categories of topics involved in the example. There was factor analysis, canonical analysis, discriminant analysis, and they did not wind up in the corners of the equilateral triangle. So in that sense, they're not the main characteristics which distinguish this particular set of books. In this case, of course, the population, if you want to call it this, is very loosely defined. It's stated in Gifi, it was the set of multivariate analysis books that happened to be in the library at the time, and that was not lent out. So the population is defined in that sense, but it's not very responsible. It's not let's say, an example of how you would go about studying a serious scientific problem, because there you would have to worry about how representative these books are. And it is my idea that if you add the new books, and even if you use all books on multivariate analysis that exist at the moment, would still be a difficult problem, because there was a borderline between multivariate analysis and non-multivariate analysis books, that not very much different would come out of the analysis. So in that sense, I think I'm sort of implying that the results can be generalized to, as long as you're keep using my categories, of course. You must not redefine the categories in which you distribute the pages of the book.
But taking out the one book on the corner would have changed.
Well, actually, that analysis is also in Gifi with the one book on the corner taken out. And what happens is that the first dimension disappears, but the relative position of the other books remains completely the same. So it does change the analysis in the sense that the first analysis disappears, the first dimension disappears, and the new first dimension is the old second dimension, and the new second dimension is the old third dimension. So it has a predictable effect on the solution, and it doesn't. It's the rest of the point is stably located in the three-dimensional space. That's another way of putting it.
And that book is called Multivariate Analysis.
Yes, it is.
It's a very confusing book. It's
It's not written for a linear algebra course in the mathematics department. It's written for researchers.
Yes. Well, the fact that it is a strange book is another thing which comes out of the analysis.